Hello everybody, my name is Eduardo Tominaga. I'm a PhD student at the University of Oulu, where I work with the Machine Type Communications group. And in this video, I'm going to present a short presentation about one of our most recent works, the paper Network Slicing for eMBB and mMTC with NOMA and Spatial Diversity Reception. And this paper was accepted for the next edition of VTC. In this paper, we study an uplink scenario of a 5G network where a massive number of machine-type communication devices and an eMBB device are transmitting in the uplink to a common base station. All the devices are single antenna devices, whereas the base station is equipped with multiple antennas. The eMBB and massive mMTC traffic share a radio resource that is composed of one time slot in a single frequency channel. And in this paper, we study two different networking slicing strategies, that is, the slicing of this radio resource. Under the orthogonal slicing, a fraction alpha of this radio resource is allocated for massive mMTC traffic, while the remaining is allocated for eMBB traffic. On the other hand, under the non-orthogonal slicing, the traffic from both services overlap during the whole time slot. And the main point of this paper is that under both slice schemes, we use non-orthogonal multiple access to allow a massive number of massive mMTC devices to transmit simultaneously. And the base station, in order to recover the multiple overlapping signals, performs the seek decoding. To evaluate the performance of both slice schemes, we first plot the pairs of maximum achievable per device data rates in bits per second per hertz. In the x-axis of this figure, we have the eMBB data rate. In the y-axis, we have the mMTC data rate. And for this figure, we set 1 mBB and 10 mMTC devices transmitting to the base station. An average received SNR for eMBB of 20 dB, average received SNR for mMTC of 5 dB. Then we also set the reliability requirements of 10 power to minus 3 and 10 power to minus 1 for eMBB and mMTC respectively. The continuous curves corresponding to the non-orthogonal slicing, the dashed curves for the orthogonal one, and we plot these results for increasing numbers of receiving antenna elements at the base station. And our main finding is that the more we increase the number of receiving antenna elements, the more advantageous the non-orthogonal slicing becomes when compared to the orthogonal one. For example, for L equal to 1 or 2, the orthogonal slicing is always better. But as we increase L, the number of antennas, we see that the non-orthogonal slicing allows us to achieve some pairs of data rates that are not possible to achieve with the orthogonal slicing. Here we have a similar result with the same parameters, but now we set an mMTC data rate of 0.25 bits per second per hertz, and then we plot the maximum number of mMTC devices that can transmit simultaneously while still satisfying the reliability requirements of both services, and we plot this versus the eMBB data rate. And even though it's a different result, we also have the same conclusions from the previous figure. The more we increase the number of receiving antenna elements, the more advantageous the non-orthogonal slicing becomes when compared to the orthogonal slicing. Thank you very much for watching this video, and please check our paper that was accepted for VTC 2021 spring.